Rudvij, my man, how's Rainbow Six doing? You winning?
His mic's muted. He can't hear you. Or see you for that matter.
Rudvij, hey, what's up? Let's hope the power doesn't go out today.
Sorry, Professor, my headphones weren't connected to Zoom.
Oh, is that how it is?
Yeah.
You're connected to Rainbow Six, weren't you? Killing it? You're winning? Got your thumbs of thunder going on? You gonna play us a little serenade on your guitar? No? No one else wants to show their faces. That just plain hurts. Makes me sad. You know, I got today, Tuesday, and next Thursday to see you all. There you go. That's what I'm talking about. Let's see some of those faces. Minsung, Brian. Brian's growing a beard. He's just like letting it all go. I shaved today. Not very well. Atria looking as beautiful as ever. Minsung, you look like you just woke up.
I just took a shower and just, yeah.
Oh. Very nice. So how were you able to patch me in, Minsung? How'd you do that last time?
Oh, cause like I had your number, cause like you gave us like your phone number.
Yep, I know that you called me, but how did you connect me to everybody else?
Oh, I just like make a speakerphone on my phone, and I just like put it close to my laptop.
Ah, okay, that worked. I was wondering if you had some special technique where you patched me in and did some kind of low tech
technology.
It's very low tech magic. Okay. I see. Atria, what have you been up to?
Not much.
No?
I had my last exam.
What about your last exam?
I just had my last midterm exam yesterday.
Oh, yeah? What class?
Bio.
How'd it go?
It went fine. It was really long. It was like 78 questions.
Oh, was it all multiple choice?
Yeah, it was all multiple choice.
How long did you have to do it?
1 hour and 30 minutes.
Oh.
Yeah, it felt kind of short, but it's okay. Whatever.
Yeah, I've been thinking about the exam for you guys, and I think 100 questions in 2 hours might be pushing the limit. I think that might be a little, especially if there's calculations. So I think I'm gonna make it less, maybe more like 50 questions.
That's great. 50 is perfect, I think.
And I'm also thinking, you know what, not giving you partial credit is kind of hurtful too. So I think what I'm gonna do is, clearly I'll just want the answer sheet, but on questions that require calculations, if you do show work, I'll give you partial credit. So if I give you 50 questions, each one's worth 2. If you show work, I'll give you 1 point. I don't want to change it so dramatically that, you know, you're used to having partial credit and then all of a sudden I just cut it off, and that wouldn't be right. Oh, people are showing up, checking in. Checking in. Brian, who are you talking to?
Rubich.
Huh? Rubich?
Talking to him, man.
Are you guys like in the same room?
No.
No, we're on Discord call.
You're on what?
Discord?
It's this app that people use to like get in calls and whatnot whenever they're streaming and stuff.
Discoid. Interesting. What's up, Cedar? You look comfy. Hi, Raylene. Good to see you. Jorge, you got your avatar up there with the oh, there you are. You went old school. Let us see your face. That's good. Yeah, we got a couple more chances to get together, and then it's going to be over. Have you gotten any word? I haven't. Is Cal State going to be remote in the fall or no?
I think we are going to be remote for at least the first half. And we're going to see about the second half.
Because my college, like I told you guys, is officially going to be remote. And my neighbor who teaches at Santa Ana said they're going to be completely online, not just remote, but online. Oh, that's not good.
I don't know if it would be remote or online. I hope it's not online.
I'm gonna push for certain classes to be in person though. My biotech, that program, I mean, that's all about dealing with this whole kind of scenario, right? Put gloves on, put a mask on, social distance. So I'm gonna try. But other classes like tech and engineering, you can't do welding remotely. You can't do welding online. You got to come in person. And so we have to figure some things out for in person with social distancing. But I don't know. I don't know how that's going to work. My chemists are all putting together kits to mail to students, so that's going to be interesting. And I get emails from students like you every day. Dr. Hartmann, please let me take Chem 111A. I don't meet the prerequisite and I can't take the exam, but let me in anyway. No, I can't. But the enrollment's actually pretty strong. I have, I think, 9 sections of chemistry this summer and like 90% full as of this morning after a week of registration. So I don't know. What are you guys' thoughts on this whole continuing education in this format? Are you going to stick with it or are you just going to like hang it up and say I'm done for now?
Like, I can't afford to like fall behind, so I just like have to roll with it. So
You going to stay enrolled at Cal State or are you going to take classes in a community college?
I'm gonna stay enrolled at Cal State, and then I'm taking 2 summer classes to like.
Oh, yeah? Where are you going for summer classes?
I'm just gonna do online at Cal State because they don't have them at the community. I would want.
What classes?
It's like Theater 101, and then this other class I forgot the name of. I'm just taking it because I need it.
Sure, some gen ed stuff. You got to get it out of the way. I get it. Totally get it. Absolutely. All right, looks like 27 of you are here. That's, enough for us, I think, to get started. So I only heard from one of you about the exam. Does that mean all the rest of you were happy with your scores and you didn't want any more points? I'm fine with that, but okay. For all the rest of you that just showed up, let me reiterate what I was saying as I was waiting for you to sign up. So 100 questions on a multiple choice exam for the 2 hours we have. I've decided that that's just way too long, especially as I was starting to look at questions I'm going to ask. And I'm thinking, okay, if I ask you to do like an excess limiting calculation, anytime I ask you to do calculations, it's probably going to take you more than 1 or 2 minutes to do that question. And if you have 2 hours, that's 120 minutes and 100 questions, that's like a minute and 20 seconds or so for every question. That I can't do that to you guys. So it's going to be 50 questions at the most. It might be a little bit less, but it'll be at the most 50 questions. And I've also decided that I'm going to give you guys partial credit for the questions that require work. So what it'll be is that essentially you'll just need to take a picture of your answer sheet. So there'll be the exam. I'll email you the exam with all the questions. And then you'll have an answer sheet where you write your answers. And if you want to show work for any of the questions that required work and potentially get partial credit, you can also send me a separate page with your work. And then on any question that required work, like a calculation or something, if you get it wrong but you showed work, I'll give you half credit. Okay, so I want to make sure that you have at least some continuity in the grading, so I'm not just like completely cutting you off and not giving you partial credit anymore. I've been thinking a lot about that, and I think that I'm not interested in making that harsh of a transition. So there you have it. Okay, so I did start putting together the final exam. No, Bianca, our exam is not Tuesday. Our exam is on Thursday. We actually officially, today is officially the last day of class. Tuesday, I'll be here to answer your questions, but it's not officially a class. Classes end Saturday. The 8th is the last official day of classes. And so Tuesday, I will open up a Zoom session at 5:30 to answer questions. And if nobody has any questions, well, then that'll be it. And then Thursday, remember the exam on Thursday is from 5 to 7. It's not from 5:30 to 7:30. So everyone has to make sure that you log in at 5. And I'll send a special Zoom link for the final exam. I'll email with a reminder to all of you so that you remember that it's at 5 o'clock and not at 5:30. Okay. Anyone else? Any other questions? So my iPad had a little crack in it and I dropped an apple on it. And now I dropped an apple on my iPad. I don't know if you can see that. It's all cracked.
Oh my gosh.
So I think the pen still works, but this is a school iPad. It's not mine, and I think they have Apple Care. So whenever Apple gets back into business, they'll put a new screen in it. But I grabbed these from the physics department when we went remotely. I have like 7 more of these in my bedroom. So if it came down to it, I did look before class. I'm like, okay, I paid for Notability on this thing. Can I transfer it to a new device? And I think you can. You got to go to the cloud and do that. Yeah, I am not very tech savvy. So, by the way, thank you to Cindy and Min Sung for calling me on Tuesday when my power went out and figuring out the way to do that. I appreciate you guys reaching out immediately because I was sitting here thinking, what just happened? And I didn't have any idea of how I was going to get a hold of you guys. And then lo and behold, some of you contacted me. So that was pretty awesome. So thank you for doing that. I really appreciate you making that offer. Okay, so no other questions? Any other questions?
Professors, actually I have questions.
Hey,
Sorry.
Sammy, of course you have questions. You always have questions.
Yes. Sorry.
Yeah, what's up, Sammy?
Yeah, so I'm taking 128 next semester, and do you know like what are they doing with the lab?
Did you get into it?
Yeah.
Wow, I have no idea what they're doing with the lab. I can tell you what my people are doing with lab. We're working with a company in Florida that puts together kits. And any student that registers for our chemistry class, once like a week and a half has passed, if you stick it out and don't drop, you'll get a box in the mail and you'll have labs that you can do at home. That's what we're doing. I have no idea what Cal State is doing. If you want, I can send an email to the department head and ask him.
Yeah, if you can, please.
Okay, Sammy, for you, I will do that.
Thank you very much.
I'm just going to send an email to myself right now as a reminder, so talk amongst yourselves.
I have a friend who's taking it right now, and so far they're just doing like, those online things where you drag.
Virtual labs, I hate that stuff.
They're doing virtual labs right now. I don't know for fall.
Okay. So I sent that email to myself, and I will do my best to remember to ask the chemistry department what they're doing. Any other questions, Sammy?
No, I'm good. Thank you so much.
Okay, Sammy, we got to do our little thing. I haven't done that for a while. How you doing?
Yeah,
I'm
Dr.
doing
Hartmann.
fine.
Come on, I'm doing all right. How you doing?
I'm
Dr.
doing fine.
That's funny.
Hey, Dr. Hartmann, can you hear me?
Yes, I can hear you, Marlo. How's it going, man?
Good, good. Can you find out what they're doing for summer for 128?
I most certainly can. Let me send that to myself as an email as well.
Thank you.
So Marlo, you want to know what's happening with 128 for the summer?
Yeah, because I'm taking it for the summer and everything got transitioned over online. So I just want to see what I'm getting myself into.
Okay, so you did get in.
Mhm.
All right.
Thank you.
No worries.
a question too.
Yeah, Daniela, what's up?
So I know that you sent the email out saying that the chapter 13 homework is it gonna be like not included in our grade? But if we already did one of them, is that not included either way?
If you already did one of them,
Yeah.
well, who's showing me my face, Ramon? That was pretty funny, Ramon. Sorry, made me completely lose my train of thought. Thank you. Appreciate
Yeah,
that.
sorry. That was kinda
No
weird.
worries. Daniela, I don't know if I can go in there and tweak just one person's grade, but if you send me an email and say, hey, I did this and I want credit for it, my guess is it's probably not going to impact your homework percentage very much, but send me an email, I'll look at it, and if it helps your homework percentage, I'll include it for you.
Yay. Okay. Thank you.
Yeah, but not for Andrew, not for him, no way.
Wait, what'd you ask Daniela? Wait, what
She
would you
said
include?
she started. Remember, there were two homeworks. The last two homeworks.
Oh, the ones that you took off.
Yeah, she had already
Oh,
done
okay.
one of them and was hoping to get credit for it.
Oh, I see. Okay.
Yeah. Chris,
All right.
how your glasses doing, Chris?
Good. They're good. I still have that one
I
pair.
wouldn't know because I can't see you.
Oh, okay. Hold on. Let me turn on my video. I just finished playing basketball outside, so I'm all sweaty and stuff. But,
Well, what? Cares? Nobody can smell you. It doesn't matter.
you never know, man. I've been playing hard outside. It's hot.
Really?
Like coming through the screen.
It's the best time. I like this. I mean, I like to run when it's hot out. I figure if I'm going to run, I want to get sweaty. And so this is nice hot weather. I can work on my tan. I can get a run.
Have you been running?
Every other day without fail. Yeah.
Hell yeah. Nice. Getting that exercise.
We had a nice ribeye for dinner last night, man. It was, oh yeah, you gotta.
Damn. Kind of sad I didn't get an invite though.
Oh yeah, I know. When this is all over, I suspect there's gonna be a lot of serious partying going on.
Right.
And it's sad. It's weird not seeing my faculty or my staff on a regular basis. I'm just like, what's really sad is okay. So we are remote for the fall, and the letter from my chancellor hinted that we might not even be back on campus till March, which is bizarre for me to think about. But the problem is I'm human like anybody else, and I haven't set an alarm for since March. Yeah.
Fine. You're chilling.
Oh, yeah. Well, yeah. The best sleep ever is when you know you don't have an alarm to wake you up. I mean, I wake up around 7:30 at time for my normal work hours anyways, but I don't have to worry about getting up at 5, run at 5 till 6, then take a shower, then go to work, and then no one's it's getting done, right? Because I'm not working 8 to 5. I'm kind of working 24/7, right? I get emails all day, I get texts from my faculty all day. So it's kind of weird, but in the end I wonder if the whole world of work is going to have a new paradigm now because all employers are like, no, you can't work from home. This isn't going to work. And well, look at this. It is working with people working from home. And so I suspect it's going to be interesting to see what happens when, well, it's happening already, right? People are returning to work. I think the economy is getting fired up again. And I think a lot of people maybe a lot of people can't stand working at home. They want to get back. They don't want to be at home all day. But a lot of parents, I mean, if the schools don't open, what do you got to do? You got to stay home with your kids, right? I mean, I don't have kids. What do some of you're living with parents or grandparents or others, and you got to figure that out. So it's interesting. I will tell you that much, but we're almost there, guys. You almost made it to the end of this class, and you'll be ready to rock and roll. All right. If there are no other questions, I will, even though my class ended abruptly, I still have the notes where I left off last. So even though, like I said, between last time and now, my screen on my iPad now looks terrible.
Professor?
Yeah.
As far as the final material, is it just basically going to be everything from the beginning of the semester?
Yeah. But honestly, guys, you have to remember that the stuff that we learned at the beginning, you've been using all along, right? You've been using sig figs. You've been doing the math all along. I've been consistently giving you names of compounds and not formulas, or vice versa. So I don't think you have to cram as much as you might think you have to cram. I think you just need to make sure that you're comfortable with the material, right? In order that you can be proficient, because the final exam is 2 hours and 50 minutes or 50 questions. So you're probably going to have about 2 minutes per question. Now, some will be fast, some are going to be harder, right? Because there's calculations. So it's really about proficiency when it comes to the final exam, more than have you memorized every little thing. But yeah, it will go right back to the beginning, Chris. But I'm not going to go back and dig for like one little factoid that I told you at the beginning, right? I'm going to go through and say, okay, what was important in the early days? The early days was important about sig figs. So there will be questions like, how many sig figs does this number have? Then there'll be math. What's this answer to this math with the correct number of sig figs, right? Balancing equations. Balancing equations is kind of tricky. Some of the questions I'm thinking about, right, instead of having these are the choices of the balanced equation, it might say balance this equation and then add up all the coefficients. What's the right number when you add up all the coefficients? So it's tricky to write good exam questions that are multiple choice for that, but I think I'll find a way. But you'll have me here, right? If there's any questions during the exam, you can always ask, hey, what the heck were you thinking when you wrote this question? So, yeah. But yeah, it will go back to the beginning.
That's good. Thank you.
Sure. All right. Share my screen. Oh, come on. Guessing you don't care about my email. Look at that, right where we left off. Okay. I can see you guys on the side. I do not, let me move this a little bit and see if I can't turn the chat back on. Oh, man. Well, hopefully if somebody does some chat, it'll show up on my thing, because I honestly have no idea. Oh, wait, there it is. Here's the chat. Okay, I'm just put the chat back up. From Alec, if the question is adding the coefficients, would we add the invisible 1 in front of the equation? Well, of course, Alec, you would, because it's really not invisible. It's really a 1. So yes, Alec, can answer your question. If the coefficient is 1, you would count it. Yep. Okay, so if you remember what we were talking about last when we left off is the shapes of molecules. And just to kind of refresh your memory a little bit, remember we started with something simple like silicon tetrachloride, and we talked about the shape that you draw when you write it on paper like this. This shape is deceiving because it looks like it's flat and it looks like it's a planar, and so you might be tempted to call that 90 degrees, but in real life it's not. We're stuck with yes, of course it's going to be on the exam, Nick. Come on. Yes, this stuff is so this stuff is included, and that's why Tuesday you can ask questions, right? This is actually not that complicated. It's relatively easy to understand, right? So when you're looking at shapes, and when you encounter a question about shape, you'll notice that you start with a formula, but before you say anything about a shape, you have to draw a dot structure. So I want to stress that to you guys, is that when you're asked about shapes of molecules, the first thing you always want to do is draw a valid dot structure, all right? Because the dot structure is what's going to lead you to the shape. Don't guess, right? So for instance, if you look at this guy, SiCl4, you might say, oh, I got 4 things around 1. It has to be tetrahedral. That's true, right? That is true that that thing is tetrahedral, and if you guess, you're probably going to get it right. But there are other things that look just like that, right? Like this, SF4. If you do the dot structure for sulfur tetrafluoride, you'll be surprised because it's not that guy, right? If we did this quickly, sulfur's got 6 electrons, fluorines each have 4, so that's 28. So you have 34 electrons to put around sulfur. If you did that, you would end up with 8 electrons in each of the fluorines. 8 times 4 is 32. We had a total of 34. There's an extra lone pair on the sulfur. So this sulfur has 1, 2, 3, 4, 5 regions of electron density on it, not 4 like this. So this is not tetrahedral, right? So be careful when you're doing shapes, don't guess, right? You really want to do the dot structure and then go from the dot structure rather than just guessing. Now, if you're in a hurry and you're like, oh my gosh, I don't have time, I got to get an answer for this. Okay, then guess. If you're running out of time, it's always better to guess than to leave something blank, okay? So if you remember, we made a distinction when we're talking about this, about the difference between the electron geometry and the molecular geometry. So the electron geometry simply looks at how many regions of electron density are in the central atom. The molecular geometry is always a subset of the electron pair geometry, all right? So in the case of 4 regions of electron density, if you have no lone pairs, the electron geometry is tetrahedral, the molecular geometry is tetrahedral. If you have 4 regions of electron density, but one of them is a lone pair, the electrons are still tetrahedral, but the molecule is trigonal bipyramidal. And we saw that with, if you remember up a page or two, we looked at phosphorus tribromide. So there's 4 regions on the phosphorus, but only 3 of them are occupied. So this molecule is trigonal pyramidal. And then we said, okay, what if you got 4 regions on the central, but only 2 of them are occupied, right? And so then we looked at the water molecule, and this is kind of where we left off. Water has 4 regions on the central atom, but only 2 of them are occupied. So it's still tetrahedral as far as the electron geometry goes, but the molecule itself, if you were going to take that 3-dimensional structure, so if you had the oxygen and you put in the electrons using the wedge and stick model, here's where all those electrons are. And if you put a hydrogen on 2 of those, right? Right, that's not 90 degrees, that is some bond angle, right? So this molecule is what we call bent, okay? So if we go back up a section, if you have a tetrahedral electron geometry, but 2 lone pairs, we call that a bent molecule, right? And then this last one should be pretty obvious to you. If you only have 2 atoms stuck together, it has to be linear, right? It's always linear. Let me give you an example of what I mean. Like a good example might be the OH minus ion, right? If you drew the dot structure for OH minus, it looks like this. Oh, these dots are kind of light. Oh my gosh, sorry about that. I need a slightly heavier pen for my dots. All right, so this oxygen has an octet, the hydrogen's happy. So if we looked at this, if we considered the oxygen as the central atom, it's got 1, 2, 3, 4 regions and 3 lone pairs. These are the 3 lone pairs. That molecule is linear, right? Anytime you have 2 atoms stuck together, it's just a line. It's a linear molecule, okay? So that's the technique that we would follow through. And these, of course, are the most common things you're going to run into, because 4 regions of electron density corresponds to 8 electrons in the valence shell. And a lot of things want to get 8 electrons in the valence shell, but not everybody's happy. And so we do need to expand that table a little bit to account for things that have less than an octet and things that have more than an octet, all right? So let's do the less than an octet first. So regions of electron density. Lone pairs, electron pair geometry, and molecular geometry. So now I'm just going to use symbols.
Good question.
Yep.
Wouldn't trigonomal pyramidal still be bent?
I'm sorry, pardon? Wouldn't trigonal pyramidal be considered bent?
Yes.
Trigonal pyramidal, all right, if we go back to something that's trigonal pyramidal, keep in mind that you have more than 3 atoms, right? So if we were just considering these three, guys, yeah, it would be bent. But you got this guy here as well. So really, the molecule is actually, right, when you connect all the dots, it's a trigonal pyramid, right? So in that case, trigonal pyramid kind of looks like it, but you aren't considering all the atoms involved. That make sense?
Yeah, I just remember last time you said that the angle decreased to like 100.
I'm sorry, you have to talk a little louder.
I just remember last time you said that the angle decreased to like 107.
Oh yeah, right. Let me back up. The angle gets smaller yet, right? I didn't mention that, but in water, right? When this, I didn't write an angle here. I believe the angle in water is 107. So it goes down even more because now I have 2 lone pairs that are squashing the remaining bond even more. So as you have more and more lone pairs, the bond angle does decrease over here, right? So yeah, it's more squashed together. So, I mean, that's just the common terminology that's used for that molecular shape is bent. I didn't make that up, but you'll run into that bent shape pretty often. Okay, so if we have regions of electron density on the central atom, you remember that there were a couple atoms that we had to worry about. So beryllium is happy with 2 bonds. Boron is happy with 3 bonds. So boron, let's see, BF, boron trifluoride is an example. So those are common examples of things that are happy with less than 8 electrons, all right? So you can kind of see the same sort of thing going on here, but it's not exactly as intuitive. So, right, so if we have 2 regions of electron density like this guy, and we have no lone pairs, right? These hydrogens want to get as far away from each other as possible. They're going to lay down in that plane. It's going to be linear, all right? There's no reason, because there's no lone pairs on this central, right? No lone pairs on beryllium. There's nothing there to distort that molecule. It's just going to be linear, right? And the molecule is also linear. If we did have 1 lone pair, right, something like beryllium, well, it's going to be hard to have 1 lone pair on beryllium. So let's, we'll just make something up, right? So beryllium would be +2. Let's make it beryllium sulfide, BES, right? So that would be, right, something like this. We'd have a bond there. We'd have a lone pair here. Even though we had 1 lone pair, I only have 2 atoms stuck together, so it has to be linear. So that one's kind of a moot point, 1 lone pair. It's still linear, and it's still linear, right? So beryllium is one of the few guys that, whatever you bond to beryllium, it's pretty much always going to be a linear molecule. If we go up a little bit, though, it gets a little more complicated. By the way, this is an example of 2 regions of electron density right here. Remember last time I also mentioned this, carbon dioxide. That's also 2 regions of electron density. Even though it's a multiple bond, and you might say, well, isn't that 8 electrons? It is, but we're not counting electrons. We're counting regions of electron density. So carbon dioxide is an example of this as well, right? That's an example of a linear molecule as well, because it's got 2 regions of electron density on the central atom, 1, 2, and no lone pairs, so it behaves like a linear molecule. Okay. You will potentially run into, maybe not in this class, because I'm really not interested in tricking you guys, you'll run into other examples when you take Chem 120A that'll be a little bit more complicated, where you have other things. I'll show you some examples of things, but I'm again, my goal is not to trick you, all right? So what if we go up to 3 regions of electron density? So let's just fill in numbers. If we have 3 regions and 0 lone pairs, 3 regions and 1 lone pair, 3 regions and 2 lone pairs, we can't have 3 regions and 3 lone pairs because then there would be nothing to bond to, all right? So what if you got 3 regions of electron density around a central atom? What does that look like? So if you got some generic atom X and you got 3 regions of electron density, physically, how do they get as far away from each other as possible? Well, conveniently, nature says the way to get these as far away from each other as possible is to lay them flat in a plane and have them be 120 degrees apart. Okay, that's actually pretty easy to view, all right? And so what do we call this particular molecule if I've got 3 things? So here's an example of a molecule that fits that bill. Remember this guy? The carbonate anion. This is only one of the resonance structures, but for looking at the dot structure, you only really need one, all right? There's 3 regions of electron density on the central carbon. That means each of the oxygens are 120 degrees apart. And this is actually a flat molecule. If you were to look at this molecule through spectroscopy, it turns out that it's flat, right? So if I had my eyeball over here, if I could get my eyeball here and look at this molecule from the edge on, I would see a carbon, I would see an oxygen, and then there'd be another oxygen right behind that carbon. I wouldn't be able to see it, but it's pretty much a flat molecule. And again, why is there nothing distorting that molecule? There's nothing distorting that molecule because there are no lone pairs on this central atom. Right? If we had 1 lone pair on that central atom, then we would start to distort it a little bit. Right? But let's go back to the names of these shapes. So if you have 3 regions of electron density, we call that trigonal planar, and this is also trigonal planar. Right? What if we have 3 regions and one of them is a lone pair? Right? What if we have 3 regions and one of them is a lone pair? How are we going to account for that? Well, again, the same story would be, what is that going to look like? So if we have some central atom X and we have a lone pair here and we have 2 other atoms Y and Y, right? Remember before, this guy, all right, let's actually put in a bond angle. Originally, this bond angle was 120, but as is always the case, lone pairs take up more room, so they're going to squash these 2 remaining guys together. They still hate each other, and there's no reason for that molecule to twist. So what's going to happen is that this is going to be, right, that bond angle is going to be less than 120 degrees, and we're just going to call that a bent molecule as well. So that's actually the second way that you can encounter a bent molecule, is if you have something that has 3 regions around it, but one of them is a lone pair, okay? And so we could go back up here and say, this is still trigonal planar. This would be bent. And I'm guessing this is going to be trigonal planar. If you have 3 regions, it's always trigonal planar. If you have 2 lone pairs, so if you have some central atom with 3 regions and 2 of them are lone pairs and one of them is an atom, you only have 2 things stuck together. It's linear. Okay? So that's actually convenient. So if I give you a question saying, what's the geometry of this molecule, and it only has 2 atoms, do you really have to think hard about the geometry?
No.
No. Why not, Min-Sung? Because it's going to be
linear.
Linear, right? If you got 2 atoms, don't even think. Just write linear. What are the chances of me giving you one with 2 atoms? I don't know. They're pretty high. You never know. For those, how many are participating today? Let me check. I'm trying to see how many people are in class today, but 34. That's pretty good. That's pretty spectacular number of students for the actual last day of class. So I'm happy to see that. Okay, what happens if you have more than 8 electrons around an atom, right? And I need to talk briefly about why that can happen, all right? So think about the periodic table again, all right? If you're gonna put more than 8 electrons into the valence shell of an atom, we need to think about, remember what we mean by the definition of the valence shell. The valence shell, right? The valence shell was the highest energy level electrons, right? The highest energy level electrons. And for the most part, we were talking about 8 electrons, which is S and P at any given energy level, right? That's where that number 8 comes from, filling S and P orbitals. The question is, how can I get more than 8 electrons into something? I can't put them in an S. I can't put them into P. Where can I put more electrons? What's the next? Yes, in a d orbital, right? 1, 2, 3, 4, 5. The d orbitals can hold more electrons. But the question you got to ask yourself, and you got to go back a little bit to think about this, when did d orbitals first become available? Well, this atom right here, right? Oops. Scandium is the first atom in the d orbital, right? What's the configuration of that? Right? This little box right here is 3D1, right? But what about these two boxes right before that?
It's 4S.
Yes, it's 4S, right? So what you got to think about is you got to think about the fact that I don't even have d orbitals available until I get to anything after scandium, right? So what's the implication of that? The implication of that is that any element before scandium, so any element here, 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 they don't have d orbitals available. So can they ever have more than 8 valence electrons? What do you think? The answer is no. They cannot. So you would never expect what we're going to call an expanded octet. You would never expect it before scandium because the d orbitals just don't exist. They're not available, right? One other thing we didn't mention also is when you're doing dot structures, there's a tendency to want to put multiple bonds in. And I don't know if I said this, and I want to caution you against it. And that is, you can't form multiple bonds before the 3rd period, right? So elements before the 3rd period are too small to make multiple bonds. And so if you drew a dot structure that, like for instance, BF, right? For some reason you wanted to give multiple bonds here. This is not possible because these guys are too small to form multiple bonds, right? We didn't talk about that. I'm not really inclined to grill you on that because it's an exception. And I think on the exam, I might have seen 1 or 2 of these sorts of things. I'm pretty sure I didn't take off for it. I just probably crossed it off and said that's wrong, but I don't think I took off for it. So I just want to throw that out there, warn you about that. It's not my goal to test you on it. So if I inadvertently do, just call me out on it, okay? So what does that mean for us? Well, we got to talk about, if my pen were going to write, more. My pen just does not want to write today. More than 8 electrons. It's called an expanded octet, and it starts after, right, the 3rd. Actually, let's not write it that way. It starts after, we'll just say it starts after scandium, okay? Nothing before that's going to have the expanded octet, okay? So what are typical possibilities, all right? So the typical possibilities we'll run into, so let's go over here again. Regions, okay, if you want to do that, I can live with that. Regions of electron density, number, this is really weird pen wants to do things I've never seen it do before. Number of lone pairs, electron pair geometry, and then molecular geometry. Okay, well, didn't want to do that either. So we did a bunch with 4, which gives us an 8. So what would be next? Regions of electron density. How about 5 regions of electron density? Right? 5 regions of electron density. Number of lone pairs, 0. So what shape do you get if you got to try and get 5 things that hate each other around 1? Okay? So imagine you've got some central atom and you got to get 5 regions of electron density around it. How do you do that? The way you do it is like this, all right? So all these solid lines are in the plane of the page. This wedge is coming out at you. This wedge is going back. It kind of looks like a top. Maybe you played with tops when you were a kid. It looks like you could spin it on there. So these 3 guys make a triangle that's in the plane, and then this is above and this is below. So those are the regions where you would put atoms, okay? And so if this is some atom, we could have a lone pair here, 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 and here. And then we could start to stick atoms on there. So the question is, what shape is that? Well, if you connect all these dots to make a shape, right, what you end up with is something called a trigonal bipyramid. I don't know if you can see it, but essentially it looks like here's one pyramid here with a triangular base, and here's the other pyramid on the bottom, right? So you Dungeons and Dragons players, right? How many faces does this thing have? Any Dungeons and Dragons players out there?
6.
6 faces, right? 1, 2, 3, and then there's 6 on the bottom, right? It's basically kind of like a 6-sided die. They get better, right? This is not the best Dungeons and Dragons dies. We always like the ones with like, what, 20 faces? The dodecahedron or the icosahedron, right?
100-sided dice.
How many?
100-sided dice.
Oh, yeah. Or like that question. Oh, it wasn't you guys. It was last semester. Never mind. I asked them a question that just totally threw them for a loop about dice. What if you had a 20-sided die, and what are the possibilities that you could get by rolling those dice? It was a statistics question. And they're like, I mean, they could do it with a 6-sided die and a 4-sided die, but when I made it 20-sided, logic just disappeared, and so I try not to do that. Okay, so trigonal bipyramidal is the way these guys arrange themselves to try and get as far away from each other as possible, right? But if you look at this, you might be smart enough to notice that not all of those things are as equally far away from each other as possible. These electrons that lie in the plane are all 120 degrees apart from each other. These electrons here and here are how far apart from each other in degrees? Anyone want to take a stab at that?
180.
So here's a pair of electrons, here's the line, here's the atom, here's the other pair of electrons. These guys are more than 90 away from each other. They are 180 degrees apart from each. Oh man, you can't even read that. I'm sorry. These guys are 180 degrees apart from each other. These at the top and these at the bottom. And then what if you wanted to compare one of these at the top to one of the electrons in the plane? Right? There's all sorts of different things in here. So what if you wanted to compare these to those? Those are actually 90 degrees apart. So trigonal bipyramidal is actually a really tricky picture to draw, and it's also kind of a complicated structure to understand. And unfortunately, a lot of molecules adopt this kind of geometry, just because when you start to get to bigger atoms, they don't want to be an octet anymore. They have other things, all right? By the way, these guys have names because they're different. Let me draw this picture again. All right, so this guy here, the ones I've drawn in blue at the top, they lie along an axis. So these two electrons are called axial. All right. These electrons lie along an equator, right? So if you imagine this as a top and you spin it along this axis, these guys just rotate kind of along this equator here. So these guys are called equatorial. Right? The axial and the equatorial lone pairs don't behave the same, right? They do not behave the same. And so when you're drawing dot structures, your goal is always to minimize interactions. You want to keep electrons as far away from each other as possible, right? And so we probably could ask that question right now. If I had one lone pair and the rest were all occupied by atoms, all right, if I had one lone pair, where would I put it? Would I put it at an axial position or would I put it in an equatorial position, right? So let's say you're drawing a structure and you got one lone pair. So here's a possibility, Y, 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 and a lone pair there. And you got this possibility, Y, 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 and a lone pair there. Keep in mind that any one of these three equatorial positions is the same. I could have put the lone pair here or here or here, all right? So if you were given a choice, what do you think? Would nature pick this as the placement for one lone pair, or would nature pick this? So we'll call this 1 and we'll call this 2, kind of like you're at the optometrist. Which is clearer, 1 or 2? 1 or 2? So if nature had to put the lone pair somewhere, keeping in mind electrons hate each other, which one would nature pick? Anyone want to take a stab?
1.
1. Why, Minsung?
Instinct.
Pardon?
Instinct.
Instinct.
Yeah.
Interesting.
It's 180 degrees.
Okay, well that instinct and 180 are both good points. Let's think about interactions, okay? Let's consider, let me pick a different color. Let's consider this lone pair right here. This lone pair sees that electron, they see the bonds, those are electrons. So it sees 3 of these guys. So it sees 3 interactions at 90 degrees. It also sees the electrons at the bottom, but those aren't at 90 degrees. Those are at, these electrons also see that electron density, and that one's at 1 interaction. Come on, pen, you can do that. Oh, it just shut off. I hope it's not dying. 1 interaction at 180 degrees, okay? So that's a possibility. Let's compare it to this guy. If we pick number 2, this electron sees this one and this one at how many degrees?
It's also 90.
Those are at 90 degrees. So we see 2 interactions at 90 degrees. And then it's got these other 2 interactions. Let me pick a different color.
2 then.
Let me pick, I don't know, what color was I using? Red. It sees this guy and this guy at what? Remember, this is 3 things in a plane as far away from each other as possible. So what's this angle here on the red?
120.
Yep, man, some geometers out there. So 2 interactions at 90 and 2 interactions at 120. So now you got to ask yourself a question. Who's feeling more interactions? Is this guy, where I have 3 interactions at 90 and 1 at 180, or is it this guy? Before you answer, let me tell you that in the interaction between 2 charged objects, like 2 electrons, is proportional to r squared. So the farther away they get, the interaction drops off by a square factor. So if you double the distance, you cut the interaction by a factor of 4, right? If you bring them closer together, you increase it by a factor of 4. If you move them apart, right? So interactions go as the square of the distance, all right? So this has 3 at 90, this has 2 at 90. The 90-degree ones are actually the most important one. So this has fewer interactions at 90 than this. So if you're going to have lone pairs, where do you put them first?
2 then.
You put them in the equatorial position, right? And that's going to kind of help you understand the shape, right? Because if you look at these, now I've jazzed up my pictures. Let me draw them again. Let's say we've got a central atom, okay? And we've got a lone pair here, and, well, actually, that's not what I meant to draw. We said the lone pair would rather be here. So let's put the lone pair there, and let's put atoms here. Y, 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 Y. Okay? Now, if you look at that particular molecule, remember if there was an X here or a Y here, so let's back up a minute. If that wasn't a lone pair, if that was a Y, I'd have 5 things around 1, so that would be trigonal bipyramidal. We named that one already. But if I make this a lone pair, right? I don't see that lone pair anymore. Now I see the molecule. I see this, this, and that. All right? So I'm not sure if you can see that in your head, what that particular shape looks like. All right? But that might look something like you encounter on a playground, right? Where you might sit here and another person sits here and you can go back and forth. It looks kind of like a teeter-totter or a seesaw, right? You can't, maybe if I turned it 90 degrees, you could see that, right? Nope, it didn't turn, sorry. Right? You could also imagine that looks something like this, where you've got Y here, Y here, Y here, Y here, and X here, right? So that shape, when you have 5 regions of electron density, right? There's still 5 regions of electron density, because that's a region. But one of those regions is a lone pair, then you only see this other stuff. We call that seesaw or teeter-totter shape. Right? If you have yet another lone pair, right? Remember we said the lone pairs want to occupy the equatorial position, so let's go back again. We want to put lone pairs here and here, which means we'll have atoms here, here, and here. Right? Still 5 regions, 1, 2, 3, 4, 5. Now 2 of them are lone pairs, so I don't look at those. I'm only going to look at the atom. Where are the atoms? So that means I'm looking at this, and I'm looking at that. Right? And again, this is off at an angle, but if you turn the picture, it looks like that, where you have X here, Y here, Y here, Y here. Anyone want to take a stab at that name? This one's easy.
T-shape?
That's it. It's T-shaped. Okay. And then if we have the central atom, oh, I don't need to change that, sorry. Same story. The central atom, it's still 5 things around it. But now we have 3 lone pairs. All right. So I've got, excuse me, I've got Y here and Y here. I'm just going to highlight it. What's that shape?
Linear.
Linear. Boom. Yep. And probably you can guess if I only have 2 atoms, the shape is also going to be linear, right? So we could go back. Now, normally, because the exam would be closed notes, closed books, these would have to be assimilated into your brain, right? Because I can't prevent you from using any resources on the exam, you know, you can have the table and you can look these up. Right? But it's beneficial for you to do these practice problems and get these things in your head, because I'm trying to prep you for the next class, and the next class will more than likely not allow you to use things and look them up. All right, so 5 regions of electron density, we call that TBP. TBP, trigonal bipyramidal. I'm not writing that out every single time. If you use this abbreviation, TBP, I'm good with that. If there's no lone pairs, then the molecular geometry is also trigonal bipyramidal. If we have 5 regions in one lone pair, right, these are always, the electron geometry is always trigonal bipyramidal. Do you remember what it was if we had one lone pair?
Seesaw.
Seesaw shaped. If we have 5 regions and 2 lone pairs, it's still trigonal bipyramidal for the electrons, but then it becomes
T-shaped.
T-shaped. If we have 5 regions and 3 lone pairs, this is still trigonal bipyramidal. I'm running into the really crappy part of my screen now. It is linear. We have 5 regions and 4 lone pairs. It's still trigonal bipyramidal, but it's also linear because you only have 2 atoms. Okay? So that's 5 regions. 5 is a very common thing to run into. So for instance, I don't know, do any of you remember when we were naming molecules, anything that had 5 things associated with one? Anybody remember anything? No?
What do you mean by 5 things again?
Something like that. SF5, sulfur pentafluoride. What do we got? If we draw this particular molecule, does this fit that bill? Right, again, you look at this and you're like, oh, 5 things around one. TBP, trigonal bipyramidal. Are you going to be right if you guess that? Maybe, maybe not. All right, so let's try it. Sulfur's got 8 electrons. Each of the fluorines has 7, so 7 times 5 is 35. Is that right? 7 times 5 is 35. Let me just make a sentence. 7 times 35. Sulfur's got, why did I say 8 electrons? Sulfur's got 6 electrons. Sulfur's got 6 electrons. So this is actually 41 electrons. All right? Is that going to work? What should bother you about that particular number?
And it's odd.
It's an odd number, right? Which means you're going to have 1 odd electron. I'm not going to draw it out, but you can see that there's no way that this thing can be trigonal bipyramidal, right? So it really behooves you to make sure that you draw out the dot structure, kind of like the one we mentioned a minute ago, SF4, right? That's the one we should have drawn, because sulfur's got 6, fluorine's got 7. 7 times 4 is 28. 6 plus 28 is 34. If I draw my sulfur and put my 4 fluorines around it, and I give them each 8, so each of the fluorines has 8, so that's 32. I have 2 electrons left to put on sulfur. And then you would say, oh, look at that. Sulfur's got 5 regions of electron density around it. So what is the shape of SF4? 5 regions with 1 lone pair makes it?
Gonna make it a seesaw shape.
Absolutely, that would be a seesaw shape, right? Now, if this was a normal exam, I would actually ask you to sketch those shapes. I'm not going to ask you to sketch those shapes. So what you would expect on the exam would be, I would say, I would give you the name of a molecule or the formula and say, what's the geometry? I'd have to say molecular geometry or electron pair geometry. What's the molecular geometry of this molecule, right? And I'd rattle off the choices and you would pick one. And if you pick the right one without doing the dot structure, great. If you pick the wrong one without doing the dot structure and don't show me work, no credit. Show me work and get the wrong one, I give you 1 point. Okay, so it's always in your best interest to do the little bit of work. And then there's one more common expanded octet. So we just did 5 things around 1. The next thing is 6 things around 1. So regions of electron density. Oh my gosh, that's totally illegible. Regions of electron. Come on. Lone, it's really being poopy. Lone pairs, EPG, electron pair geometry, MG, molecular geometry. So 6. So if we got 6 things around 1, how's that going to look? So here's my central atom. How am I going to get 6 things around 1? I'm going to get 6 things around 1 by that particular shape. So if you look at that shape briefly, you probably are seeing correctly that these guys are all in the plane of the page, right? And if you connected them, right? If you connected them, it makes a square. And if you connect these guys up here and these guys down here, that's actually not a bad picture. What is that shape? Name that shape.
Dodecahedron.
I heard somebody say it.
Dodecahedron.
Close. Dodecahedron would be 12 faces. This only has 8 faces. So what's a regular polyhedron with 8 identical faces called? Cedar? Anyone? What's the prefix for 8?
Octo.
Octahedron. This is an octahedron. So if you have 6 things around 1, the shape is an octahedron, but we call it octahedral geometry, right? So if you've got atoms on here, so if I have my atom X and I have atoms at every position, this is called octahedral. And the bond angles are nice and easy in this one too. You math whizzes, what is the bond angle between any 2 atoms?
Could it be less than 90?
It is exactly 90 degrees. 90 degrees. So all the positions are equivalent. This is a little bit easier than the 5. All the positions are identical, so you don't have to worry, oh my gosh, where am I going to put the lone pairs? It doesn't matter. They're all the same. Okay? So if you had a central atom, oops, sorry. Let me go back. And you had 1 lone pair. Let me erase this. This looks sloppy. And you had 1 lone pair. Doesn't matter where you put it. Okay, I'm going to put the lone pair right there. What does that leave me for a shape? Well, I've got to put my other atoms in. So Y, 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 Y. Right. These are all in the plane of a page. This is below the plane of the page. So if you connect all those faces, you get a square pyramid. So octahedral with 1 lone pair is called square pyramidal. Okay. Square pyramidal. What if you have octahedral with 2 lone pairs? Well, same place. We start with our central atom. Just draw out the rough geometry. Because every place is identical, I'm going to pick the 2 easiest spots to put my lone pairs. Just put my atoms here. All right. These Y atoms are all in the plane of the page. So if they're flat in the plane of the page, what are we going to call this?
Linear.
Well, it'd be linear if they were all in a line, but they're not in a line. Remember when we had 3 things and it was all flat? Remember what we called that?
Plane.
Trigonal planar. Now we have 4 things and they're all flat. Now what are we going to call it?
Just a planar.
Almost. You got to tell me there's 4 things somehow.
Tetraplanar?
That's a good guess. What shape is this?
Square.
That's the answer.
Square planar.
Square planar. That is the shape when you have 6 regions and 2 of them are lone pairs. All right, what's the next one? Well, 6 regions and 3 of them are lone pairs. So we make our central atom. And again, all the positions are identical, so it doesn't matter which ones I pick to make my lone pairs. Okay, so now you look at this and you just basically connect these guys and ask yourself, what shape do I get if that's what I've got left? All right, and you might be thinking about distortion. You might think this guy is distorting the shape. It might distort it a little bit, but not very much. So what does this look like? I'm highlighting it for you to make it easy.
Another T?
It looks like a T shape. Right? So if you've got 6 things around 1, the electron geometry is octahedral. If you have 3 lone pairs, it becomes T-shaped. Right? It gets easy from now on. If I get another lone pair, who's going to predict what the shape's going to be if I throw 1 more lone pair in there?
Become linear then?
Pardon?
Does it become linear then?
It is going to become linear, yep. So if I do the same thing, and it may not be entirely obvious to you depending on how you draw it, right? You might draw that and you say, oh, you know, that doesn't look linear. That looks like these guys are bent, all right? But you could equally have as well have put the lone pairs here, right? They're all identical, right? And so if we had atoms here, Y and Y, right, that's linear. And then at that point, we would only have 1 more to go, and we'd only have 2 atoms, so it becomes linear again as well. Right? So that would fill in the rest of that table. You have the answers. I don't think I need to go back to that table. But that's the idea, right? The gist of molecular shapes. And doing molecular shapes, it's hard for me to say why this is super critical. It's important later on in chemistry because the shape of a molecule is super important in determining a lot of its properties. So later on, we do spectroscopy on these molecules, and the shape is related to how they vibrate. It's also important in how these molecules behave. And so if you think about some of the drugs you might take, like aspirin or ibuprofen, or maybe you're on a prescription drug, the shape of the active part of that molecule is important because it fits into a receptor in your body. Right? And that localized shape is governed exactly by this sort of thing, right? Even though the molecule might be huge, you might have this big protein, and then right down here at the end of that protein, you might have something like this, right? And this is the active part of the molecule, and the shape at that point is really important because that's the point that binds with the protein and changes the behavior in your body, right? So localized geometry is really important. It may not seem important in this class, but it's a fundamental thing that scientists use to describe how molecules interact and react with each other. The other thing that's important for this is related to what we started to hint at, and that's related to electronegativity. Right? So you might not remember electronegativity. You might remember the periodic table, and you might remember that electronegativity is really high over here. Actually, let me make that red. It's really high over here, and electronegativity is really low over here. So low and high, right? To refresh your memory, electronegativity deals with the pull on bonded electrons. So for instance, if I've got the O2 molecule, these electrons right here, because these atoms are identical, these electrons are shared evenly between the two oxygens. If, however, you have two different atoms, like let's say you have H bonded to Cl, all right, these electrons are not shared evenly between the two atoms, right? In fact, these electrons are moving. They spend way more time on the chlorine than they do on the hydrogen, right? So I'm trying to draw a picture that represents a million flash pictures of these electrons. Keep in mind, I can't see electrons because once I observe it, I change its path, right? And I would predict that if this pair of bonding electrons spends more time here and less time here, this positive nucleus on this hydrogen is going to become exposed a little bit, and that end is going to appear to be slightly positive, and this end is going to appear to be slightly negative. So I just threw that out there. This is the Greek letter delta. It's a lowercase delta, and it means partial, right? So what you're going to be able to do with this concept of electronegativity is to look at any two bonded atoms and ask yourself, are electrons shared evenly? And if they're not shared evenly, where do they spend more time, right? I know you guys like formulas. You'd like to say, okay, if I looked at the table and let's say the electronegativity of fluorine is 4, I should probably pull up a table of electronegativity. So let me actually stop sharing this. Let me go back to my desktop and let's pull up the can I spell I can't spell, but I found a table. Let me get the table. And once I get it, I will take a screenshot of it because that's how I roll. I'm just sick of trying to send this stuff to my laptop, to my iPad. Okay, now let me send that to my iPad whilst you guys talk amongst yourselves. All right, so let me share AirDrop to my iPad. Accept. Okay, done. Done. Let me share my screen again. And there you have the wonderful table of electronegativity values. Okay? And so this is not something I expect you to memorize. You can look it up at your whim. You'll need it to answer questions about things. But this is going to become really useful in terms of you thinking about, are the electrons in a bond shared evenly, right? And you might not care about that, but if they're not shared evenly, then the bond becomes polar and the molecule can become polar, and that really changes a whole lot of behaviors. It really explains a lot of things like, why don't oil and water mix? They're both liquids, so why doesn't oil dissolve in water? Well, it's because oil is nonpolar and water is polar, and they don't like each other. But if you look at this particular table, so I had drawn up for you, oops, my thing is not done here. So let me just share this with Notability and add it to my current note, import, done. I almost had it, but not quite. All right, so there it is. Let me move this right here and let me expand it. I'm telling you what, I'm learning some skills here. Really, really impressed with myself. Okay, so if we had HCl, if you look at this electronegativity table, I don't want to use red because that's an ugly color. Fluorine's got a value of 4. Hydrogen's got a value of 2.1. Right? They're just numbers, okay? Nothing to worry about. What you should pay attention to, though, is 4 is the biggest number on the table. And 0.7 is the smallest number on the table. Right? So every atom has some desire for bonded electrons, but fluorine has the most. What you should also notice is that these guys up here, not the noble gases, just the halogens and the nonmetals over here, they really like electrons. Why do they really like electrons? Anybody?
They're one electron away from being a noble gas.
Absolutely. And why does fluorine, of all the elements on the table, really, really, really want electrons? It's one away from a noble gas, and it's really
Small.
small. Absolutely. So those are the kinds of questions that also will kind of be brewed into some of the multiple choice, right? I might say, you know, why does fluorine have the highest electronegativity? Something like that, okay? These are experimental values. You don't have to worry about how they're determined, all right? But they're numbers, and they're all, not all different. They're very different. But what you can see is the two that I've picked, hydrogen has a value of 2.1, chlorine has a value of 4.0. So when you're asking yourself, okay, what sense do I make out of this? The first question you ask yourself is, are the electronegativity values different? So I'll ask you, are the this is an easy question, super easy question. Do hydrogen and chlorine have the same electronegativity values?
No.
No. As soon as you said no, what that means is that this bond is polar, right? If the electronegativity values are not the same, the bond is polar. I don't want you to worry about degrees of polarity at this point. I just want you to know that if the numbers are different, the bond is polar, okay? That means they don't have the same desire for electron density, right? Can you pick a bond between two atoms that are not the same that wouldn't be polar? Think about this. Hydrogen's 2.1, phosphorus is 2.1. What if I make a bond between hydrogen and phosphorus? Do they share electrons evenly or unevenly?
Evenly.
Evenly, right? Because they have the same value of electronegativity. So even though they're different atoms, they have the same electronegativity, so that bond is not polar, all right? So the next thing you want to ask yourself is, what is the En difference? This is simple subtraction. Simple math. 4 minus 2.1 equals 1.9. This is just a number. It doesn't mean anything by itself, but if I asked you to compare several different bonds and rank them according to polarity, that's what you would have to do, okay? So you would compare them. So let's say I'm comparing the hydrogen-chlorine bond to the hydrogen-fluorine bond, right? I'm pretty sure you can already tell me which one's more polar, right? Which one's more polar, hydrogen-chlorine bond or hydrogen-fluorine bond?
Hydrogen fluorine.
The hydrogen-fluorine bond, right? Because this is still 2.1 and this is 4.0. Oh, you know what? Nobody caught this, and you didn't correct me, and now I have to go back and fix
Fluorine
it.
should be 3.0, right?
Chlorine should be 3.0. Minsung, why didn't you correct me earlier?
I was like, maybe there's some reason why you wrote like that.
Yeah, dude, fix it when I make a mistake like that. Look smart. Take every opportunity. Anyone out there catches me making a mistake. All right, the difference between 3.0 and 2.1. 3.0 minus 2.1 is 0.9. 4.0 minus 2.1 is 1.9. So the difference is 1.9 in HF. It's 0.9 in HCl. That means that the HF bond is more polar, more unevenly distributed, however you want to phrase it. It just means it's a more polar bond. Right? There's a lot of ramifications for that, but that's what you would do. So if I arbitrarily asked you about the bond polarity, so let's pick a molecule like water, right? And let's draw the dot structure for water, right? And I put the bond angle in there just because I'm used to doing that, right? I might ask you, all right, is the bond in H2O polar? Now, do you have to do the math to tell me that the bond in H2O is polar? Do you have to do the math? What do you think?
Yes.
Well, in principle, you would have to do the math, but if you use this table enough, you're probably going to get used to knowing what some of these numbers are. Oxygen's 3.5, hydrogen's 2.1. That bond is definitely polar, okay? Now what you're going to have to start thinking about is, okay, this bond is polar, and this bond is polar. But I'm only at this point talking about the bond. You might say, why do you keep saying bond all the time? Why do you keep saying, is it because you like saying bond? No, because I'm going to differentiate between a polar bond and a polar molecule. Oh my goodness. What just happened there? Isn't a molecule polar if the bonds are polar? You might scratch your head and say, well, yeah, of course it is. Well, no. I wouldn't make the distinction if that was always the case. So let's go back to water, right? We know the shape of water molecule is bent. And we know that these bonds are polar, and I can indicate that in one of two ways. I can use the delta symbols I just mentioned earlier, delta negative and delta positive. Right? This means partially negative, this means partially positive. Or I can use this terminology. This is a dipole indicator, and a dipole simply means it has two poles, right? So you would draw an arrow like this, where this is the positive end of the bond, and this is pointing towards the negative end of the bond. So let's go back to our water molecule. Where are electrons going to collect? Are the electrons going to collect on the oxygen, or are they going to collect on the hydrogen?
Oxygen.
Yep, so the oxygen becomes partially negative, and the hydrogens become partially positive. I'm going to go to a new picture and draw it over again. So that's one way to draw the bond polarity in the water molecule. Another way is to use those dipole arrows. Oh, that was not intentionally shorter. That was my cracked iPad screen. Oh my gosh. Okay. What if I had to put the dipole arrows into this particular molecule? What would that look like? It would look like this, where I'm indicating those dipoles, okay? Now remember, this molecule is bent, okay? It's bent. But let's just do something for fun. What if I had some generic molecule that looked like this and had those same kind of arrows where they were pointing towards that central one? And instead of thinking about dipoles, right, imagine that this was a ball and these are forces, identical forces pushing on that ball. Is this ball going to move? What do you think?
No.
No, why not? What happens with these two forces?
Cancel each other out.
Cancel, right? It's a little bit of physics. Sorry, I'm throwing some physics in there. This is for you, Marlo. These guys cancel, okay? Now, if you go back to the water molecule, are these guys pointing exactly at each other? What do you think?
No.
No. So will they cancel?
Nope.
No. So what that means is that this molecule has polar bonds, and those bonds, because of the shape of the molecule, don't cancel. So this overall molecule is a polar molecule. All right? It's a polar molecule. That's really important. The fact that water is polar is super important. In fact, life as you know it would not exist if water was not polar, right? Water is a really good solvent. Water expands when it freezes. All these things are related to the polarity of water, right? If water didn't expand when it froze, right, lakes would freeze solid in the wintertime. All life in those lakes would die, and eventually a lot of life would die, right? Things would be completely different if water wasn't a polar molecule. Let me give you an example where they do cancel out, one that's a little bit easier to see. So if we did the CO2 molecule, remember CO2? We drew that earlier. Let's not even refer back to the table. Let's just use our brains and our understanding of the periodic table. You got two atoms here, carbon and oxygen. Which one of those atoms likes electron density more? Just think about their arrangement in the periodic table, right? And if you can't remember the periodic table, CNOF. Which one of those, carbon or oxygen, likes electrons more?
Oxygen.
Oxygen, absolutely. So without thinking too hard, I can do this. I can do those two things. Right? But remember the geometry of carbon dioxide. I have two regions of electron density on the central atom, and both of those regions are occupied. So what's the shape of carbon dioxide? Do you remember?
Linear.
It's linear. So what happens to these two dipole moments of polarity pointing in opposite directions? If you can't think about it in terms of dipoles, think about it in force. You got a ball, and you've got forces pulling, identical forces pulling in opposite directions. Will that ball move?
No.
So what happens to these forces?
Cancel out.
So what happens to these dipoles?
Non-polar molecule.
They cancel out. So here's an interesting development. This bond is polar. Electron density is unevenly shared between carbon and oxygen. Right? The oxygen gets way more of the electron density than the carbon. And so if you looked at it from a distance, the oxygens appear to have an abundance of electron density. But if you zoom farther out, like you're on Google Earth and you take it a couple levels out and you look at the whole molecule, that molecule appears to be non-polar. Right? It appears to be non-polar. Right? That's the beauty of molecules. You can look at the bond and make an assessment about the polarity of a bond, and then you can look at the molecule and make an assessment about the molecule and its behavior, right? And that's related to a whole bunch of other stuff, right? We're not going to have a ton of time to get through those, so I'll make sure that I don't ask you questions about those. But, right, why is water a liquid at room temperature, right? Water, so H2O, it's got a mass of 16 plus 2, it's got a mass of 18, whereas NH3, which has got a mass of 17, at room temperature, this is a liquid, this is a gas. Why is that? Why is water a liquid and why is ammonia a gas? It has to do with the fact that water molecules are really polar, and if you have one polar molecule next to another polar molecule, what are they going to do?
Attract each other.
Attract each other, right? So those intermolecular forces are going to hold it together very strongly and make it want to be a liquid or even a solid rather than a gas. Okay? And so that idea of polarity and bond polarity is related to that topic of this thing that we call intermolecular forces. Not to be confused with intramolecular forces. These are forces within a molecule. Think bonds. These are forces between molecules. Right? Forces between molecules. Let me give you an example. We'll stick with water again. Remember, the water molecule is polar. So if I bring another water molecule nearby, this negative is going to orient itself towards that positive because it likes it, right? And all the other water molecules in the liquid are going to do that. So there's some degree of attraction between these molecules, right? They're going to want to hold together. If I drew the picture of ammonia, if you drew the dot structure for ammonia, you'd end up with this. You got 4 regions of electron density, so the electron geometry is tetrahedral, but only 3 of them are occupied. Does anyone remember what that shape is? What's the subset of tetrahedral where you have 1 lone pair?
No.
Trigonal pyramidal.
Yep, trigonal pyramidal. All right. So then you got to ask yourself a question. What about the nitrogen-hydrogen bond? Is this electron density shared evenly between nitrogen and hydrogen? You don't have to memorize the electronegativities. You just got to think about placement in the periodic table. But I'll go back to the electronegativities just because you may not know that yet. Let me erase some of this scribbling on here. So nitrogen is 3, hydrogen is 2.1. Do they share electrons evenly? What do you think?
No.
Nope. Which one gets the electron density more between nitrogen and hydrogen?
Nitrogen.
Nitrogen. So if we were going to put these in terms of the dipole, you got that dipole, you got that dipole, and you got that dipole. But the question you need to ask yourself is this bond here as polar as the oxygen-hydrogen bond in water? What do you think? No, they're not as polar. So this ammonia molecule is not as polar as water. So the attraction between ammonia molecules is not as strong. And so at room temperature, it's a gas rather than a liquid. Right? The stronger the intermolecular forces, the more likely it is to be a liquid. If they get really strong, it could be a solid. So the forces between guys. Now, there's actually several kinds of intermolecular forces that you need to be aware of. The first one is called dispersion forces. Right? Dispersion forces are forces of attraction present in every substance, right? Every substance exhibits dispersion forces. And how do these forces originate? Well, let's say you've got an atom, right? And we'll put a few protons in the nucleus, and we'll give it some electrons out here. Those electrons are constantly moving, right? How they're moving, we don't know, but we know they're moving, right? And they tend to hate each other, so they're always moving very, very, very far away from each other. But they're not perfect at avoiding each other, right? And at some instant in time, statistically, there is a chance that that molecule looks like this. Right? That's a possibility. It's not a high possibility, but it happens every once in a while. Right? If this happens at some given instant in time, what we have is what's called an instantaneous dipole. And if that happens, what's going to be true about a molecule that's sitting next to it? Well, if this guy looks slightly positive over here and slightly negative over here, there's going to be some attraction between these guys. It's not necessarily going to be strong, but there's going to be some attraction, right? Every atom exhibits this. So there's a force of attraction between all molecules, no matter what, right? And dispersion forces parallel the size of the molecule. What do I mean by that? If the molecule gets bigger, the dispersion forces get bigger. All right. Why is that? Because the bigger the atom gets, the fuzzier it gets. It's hard for the nucleus to hold on to electrons in a big atom. And so they can move more freely, and there's a bigger chance that they will be all on the same side at the same time. Let me give you an example of what I'm talking about. In the periodic table, the halogens, we have fluorine, chlorine, bromine, and iodine, right? Remember these guys? And as elements, they exist as pairs, F2, Cl2, Br2, and I2. This is how they exist as molecules. So you've got FF, Cl, Cl, Br, Br, and I. This bond is completely nonpolar because they're the same atoms, they share electrons evenly. But in real life, at room temperature, this is a gas, this is a gas, this is a liquid, this is a solid. So the question is, how do you explain that? If they're nonpolar molecules, there's no polarity, there's no unevenness to cause them to be attracted. Why is iodine a solid? Why do two iodine molecules? So if I had another iodine molecule here, these guys actually really like each other so that they get together so tightly that it forms a solid. Bromine, if I had another bromine molecule, they like each other, but not quite as much. They form a liquid, so the molecules are touching, but they have freedom of motion, right? Chlorine and fluorine, not so much. They don't care about their other molecules and they stay as a gas. So why is that? Well, as you go down in the periodic table, what happens to the atoms? They get bigger, right? Iodine is huge compared to fluorine, and it's big, which means it's fuzzy, which means the dispersion forces are really, really big, okay? So if you're asked a question about dispersion forces, what you got to ask yourself is, how big is that molecule? Usually what you want to do is just calculate the molar mass, right? If you don't remember looking at the periodic table, you could just go by calculating the molar mass, right? Another one, so we've got dispersion forces, and every molecule has dispersion forces, and they're just related to the size of the molecule. Trying to go back to where my list was. I guess I'm just going to have to go to a new slide. So dispersion forces, every molecule has those. The next kind of intermolecular force, which by the way is abbreviated by this IMF, not to be confused with the other abbreviation IMF. Who knows what the theatrical movie abbreviation IMF means? You Tom Cruise fans? Nobody knows?
Mission Impossible?
Well, it's the Impossible Mission Foundation, right? Those are the ones that send Tom Cruise the message. This message will self-destruct in 5 seconds. Comes from the Impossible Mission Foundation. But this stands for intermolecular molecular forces. So dispersion, every molecule has dispersion forces. The next one that's important is called dipole attraction. All right. Let me ask you a question. What do you think has to be true about the molecule for it to exhibit this kind of force? That molecule has to be what?
Polar.
Has to be polar, right? So that's an easy one. Dipole attraction is simply an attraction between polar molecules. And how are you going to know if the molecule is polar? You're going to draw the dot structure, you're going to look at the bond, and you're going to ask yourself, is this a molecule that's polar or not, right? There's one special subset of dipole attraction, right? And that's called a subset, is the third intermolecular force, and it's called hydrogen bonding. And if it was up to me, I wouldn't use this word because I've been talking about forces of attraction, and bonding sounds really strong, but it turns out that hydrogen bonds are really strong. So what is a hydrogen bond? A hydrogen bond is a very strong attraction between a hydrogen bonded to a very electronegative atom and a lone pair. That's a mouthful, but let's try and dissect it. Hydrogen bond. Let's start with this. What element absolutely has to be present in the molecule for hydrogen bonding to exist? Easy question. It's got to have at least one hydrogen, okay? What else does the molecule absolutely positively have to have?
A bond.
It has to have a lone pair somewhere in the molecule, okay? And the third thing it has to have is a very electronegative atom. Whoa, that's really kind of vague, Dr. Hartmann. What do you mean by a very, I'm going to spell it out for you. Very electronegative atoms will be fluorine, chlorine, and nitrogen. Those are the only ones you got. Oh, excuse me, one more. Oxygen, fluorine, chlorine, and nitrogen. Those are the only ones you got to worry about. All right? So let me give you the classic example. This is water, right? Here's hydrogen. Here's a lone pair, and it happens to be on a highly electronegative atom, right? So where's the hydrogen bond? Here's the hydrogen bond. Another water molecule has its hydrogen very strongly attracted to this lone pair. This attraction right here is called a hydrogen bond, right? So let's review. It's a hydrogen bonded to a highly electronegative atom that is attracted to a lone pair, right, on another atom or another molecule, right? The nice thing about water is you'll notice that it's got two hydrogens. This hydrogen can be attracted to yet another oxygen, right? And you can see that cycle will continue. Right? Water has this ability to form multiple hydrogen bonds. That's why water is a liquid at room temperature. It has lots of hydrogen bonding. That's why water is a really good solvent. It's also why water expands when it freezes, right? You're probably all familiar with the fact that water, when it freezes, forms six-sided ice crystals. Why does it do that? Well, because when water freezes, you get the hydrogens bonding to the oxygens nearby in this three-dimensional picture, right? So here's a hydrogen bond here. Actually, let me backtrack a minute. That one, we won't call that the hydrogen bond. Okay, sorry. Okay, so this is actually a real bond here. These are the real bonds. These are the real bonds. And here's my hydrogens disappeared. So these are the real bonds right here. And so here's a hydrogen bond right here between this hydrogen and that oxygen's lone pair. Here's a hydrogen bond here between this hydrogen and this oxygen's lone pair. And here's another hydrogen bond right there. And this happens in repeated three-dimensionality, right? And so when water freezes, the fact that those hydrogen bonds line up in a particular form means that water will always freeze in this hexagonal pattern. Right? So if you've ever, I mean, it's California. I don't know if you've ever been able to collect a snowflake and not have it melt. But where I'm from, snow falls all the time. And you can collect them. If you go outside with a cold piece of glass, you can collect those and you can actually see the six-sided geometry of a snowflake. They always have six sides, right? The other thing that's interesting about this is if you kind of look at it, there's a lot of open space in this structure. And what that does is that it changes the density when water as a liquid, when H2O liquid goes to H2O solid, right? When it freezes, it expands, which means the density decreases, which means when water freezes, the stuff that freezes floats to the top. And as I mentioned earlier, that's really important because if you have a lake and the water freezes, it floats on the top and it actually acts like an insulating layer so all the fish down here don't die. If water froze and became more dense, it would sink to the bottom and lakes would freeze completely solid. And if you've ever frozen something that's living, does it make it back after it's frozen? Typically not, right? So that's really, it's actually a really important phenomenon that's related to this whole concept of hydrogen bonding, and it helps explain that, right? And then you could ask yourself questions about pretty much any property, any physical property of liquids or gases, and you can relate it to intermolecular forces, right? Why is water a liquid? Why is carbon dioxide a gas? Why is this? Why is that? So, I mean, the intermolecular forces are related to the physical properties of all sorts of substances. And it's just a matter of asking yourself a question, what intermolecular forces are here, and are they relatively strong or are they relatively weak? All righty, I have talked for a long time. I feel like I've talked forever. So I'm gonna stop sharing my screen because that's what I'm gonna do. And I'm gonna ask you all, I thought no, good answer, Nick. Ammonium, NH4 plus is the ammonium ion. That's charged already, so it's definitely going to be a polar species. All right, anyone else have any questions? All right, if there are no questions, it's very close to 7:30, which is when I normally would let you go. What I will do is I will say sayonara until Tuesday, but I will look at my email regularly. I will look at my texts. You guys have a little bit of homework left to finish. And then on Tuesday, I will just open it up to any kind of questions you might have. Does that sound okay?
Yep.
All right.
And Professor, the homework's it's not due till next Friday, correct?
Yep, I've made the homework due at like 11:59, so you can even finish the homework after the exam if you want.
Okay, perfect. Thank you.
No worries.
The exam is on Thursday?
The exam is on Thursday, yep. Thursday at 5 o'clock. Don't forget, it's not 5:30. I'm going to, as soon as I'm done here, actually, you know what? I'm not even going to wait. I'm going to go there right now, so you guys have to bear with me. I'm going to go to Sapling. I'm going to go to my titanium right now. Watch this. I'm going to share my screen so you can see what I'm doing. Watch this. Share screen. Desktop. All right, here we go. Going to compose new email. I'm going to add everybody. I'm going to say final exam, all in caps. And I'm going to say, this is a reminder that final exam is Thursday, May 14th at 5 to 7.
I think it's May 14th.
May 14th? How did I write 24? May 14th. And I can't write 7 o'clock either. 7 o'clock. All right. And here's what I'm also going to do. I'm going to go to this. Let's see if it lets me. I'm already on Zoom. I don't want to launch a meeting Zoom, so let's just go to apps. Why is it not taking? It's probably not taking me there because I'm already in Zoom. I wonder if it will. Oh, wait.
Try clicking the icon on the bottom.
App, here we go, host a meeting. So let me go to the, I'm trying to get it to let me back into my Zoom account. Sign in, that works, no worries. We'll just do this. There we go, meetings. So we don't need May 28th. I'm going to delete that. Delete this occurrence. We don't need May 26th. Bye-bye. We don't need May 21st. Bye-bye. We don't need May 19th. Bye-bye. Let's see, will it let me edit this one? It will not let me edit that one. So let me just schedule a new meeting. We'll call it final. Let's call it Chem115 final exam. Let's schedule it for May 14th. We'll schedule it for 5 p.m. We'll make it 3 hours just to be safe. We will save it. We will copy the invitation. All right. We will go back to the quick email and we'll say, here is the Zoom information. Can't spell. Command V. Boom. There it is. There it is. Send the email. You should have it. So we are now officially all set for our final exam at 5. You all have a reminder email. If I remember, I'll remember to remind you again that it's at 5. Look, if you forget and come at 5:30, I'm not going to cut you off at 7. I'll do it till 7:30, whatever. But try to come at 5 like everyone else. Okay?
Okay, Professor, really quick, is it the same meeting ID?
Probably not because I just created a new meeting and just sent it out.
I don't have that. Can you send it to me?
I sure.
Or if you can just give me the number.
Okay, let me go back to that Zoom meeting information, quick mail that I just sent. Zoom meeting information.
Sorry.
No worries. Don't feel bad. Meetings. Let me go back to my meetings. It will be Thursday, May 14th. The meeting ID is 924 8342 6889.
6889. And do you have a password for that?
I don't believe it's password protect. Oh yeah, it says meeting required. I did not. I don't think I required a meeting password.
Okay.
If it turns out you have some issues getting on, just just text me
Okay.
and we'll make sure you get on.
Okay. Let me repeat that. 9248-342-6889.
I wasn't on the page. Sorry.
Okay. Okay. No, I'll just contact my student then.
924-834-6889. Yep.
Okay. Thank you.
Awesome. Anyone else?
Professor?
Yep.
What homework chapters are you dropping?
Just chapter 13, so it would be the last 2 homework assignments.
Oh, okay.
I already made them ungraded, so you shouldn't have to worry about the chapter 13.
Thanks.
Okay? Anyone else? Más preguntas?
Could you please post like today's recording and last Tuesday's recording?
I will do my best. I don't know because of the snafu. I don't know if last Tuesday got recorded, but I think it did. So yes, I will.
Thank you.
Yep. Ramon, is that a question? No? Anyone else? Going once? All right. Awesome seeing you guys Tuesday. If you got questions between now and then, don't hesitate to ask.
Thank you, Professor.
All right.
Have a good weekend.
All right, you guys.
Professor. See you
Bye-bye.
Thursday.
Thank you, Professor.
You're welcome. Bye-bye.